Hello and welcome back. In the previous lecture, we spoke about the L1 and L2 loss functions and when should we use each, and we also discussed the advantages of each one of them. So let's just recap. The L2 loss, if we go back to this plot right here of the L2 loss, then when we reach the minimum, when we reach somewhere close to 0, when we square this result, then we get a smaller number, okay, because you're squaring a value between 0 and 1. So you'll just get a smaller value. But when the error is big, so let's say you have an outlier, the error is big, you square it, you get a larger error. So how can we eliminate this problem? Is by using the L1 loss. So basically we're going to combine the best of both. We're going to combine the advantage of the L2 loss and the advantage of the L1 loss into one other loss function called the Huber loss, or the smooth L1 loss. So what we really would like is that when we approach the minimum, then we want to use the MSE. So squaring a small number becomes smaller. And when the error is big and there are some outliers, we want to switch to the MAE, or the L1 loss. In this case, the error is linear. So we can achieve this using the Huber loss, or the smooth L1 loss. And basically it's just a combination of the L1 and L2 loss functions. So this is the Huber loss. Again, it's also called the smooth MAE, or smooth L1 loss, and it's less sensitive than the MSE. And basically, it's just the absolute error, so it's just the L1 loss, and becomes quadratic when the error approaches 0, or when the error is small. So how small that error has to be to make it quadratic depends on a hyperparameter delta. So this is basically the formula for the Huber loss. When the error here is big, so this is the error y minus fx, y is the actual output and fx is your predicted output. When this error is smaller than a hyperparameter delta, and later we're going to see the effect of tuning this delta. So when it's smaller than this delta, what we're going to do is use the MSE loss because we've approached 0. But when it's bigger than delta, then we want to switch to the MAE. So this is the MAE loss, basically. For simplicity, let's just consider that delta equals to 1. So when we have our error here smaller than 1, that means we've approached 0. Therefore, we want to use the MSE. And here there's a half just for the differentiation. Because later on in the back propagation, when you differentiate this, then this 2 comes down here. And you'll have this. Basically, you'll have this half removed, so you'll just end up with y minus fx. If you don't include the half, then when you differentiate this, you'll just get 2 times your error. But basically, it doesn't really matter. I'm just following the formulation here. So this is the formulation for the Huber loss. The half doesn't really affect, but it's of course better to follow the original formulation. So this is the MSE when the error is smaller than delta, and we said we're going to assume that delta is going to be equal to 1. And when the error is bigger than delta, so when the error is bigger than 1, then what's going to happen here is that you're going to have your MAE minus 0.5. So this, if you substitute 1 here, then you'll just get 1 times the error minus 0.5 times 1, which is basically just your mean absolute error minus 0.5. Okay, so this is the Huber loss. It's a combination of both the L1 and L2 loss. So the choice of delta is critical because it determines what you're willing to consider as an outlier. So here we said delta is 1, but now I'm going to show you the effect of tuning this delta. So this is a plot here that shows the differences between the MSE loss. So the MSE, or the quadratic loss, is just the blue plot. The MAE loss is the green plot, and the Huber loss is this red plot right here. So if we look at the Huber loss, this red plot, then as you can see, it's linear when the error is big. So let's say your error is 5, then you'll also get 5 as your output. And when it approaches 0, then as you can see, it comes to this quadratic function. So basically, you'll get a smaller result. So let's say it's 0.1. Then when you square 0.1, you'll get 0.01. So you'll get a smaller value somewhere around here. So let's see the effect of tuning delta. So this is the effect of tuning the delta. When you have delta equals to 1, you have this brown plot. When you have delta equals to 3, you have this purple plot. When you have delta equals to 5, you have this red plot, and so on. So this is the effect of tuning the delta here in your equation. So we said that if delta equals to 1, so if we're going to look at this brown plot right here, if delta equals to 1, this is the smooth L1 loss that you have. So 0.5 times x squared. Again, x is your error, y minus fx. And if it's bigger than 1, then you have your error, the absolute value of your error, minus 0.5. So this is a combination of both the L1 and L2 loss functions. It all depends on the value of delta. So here, for example, we have a delta equals to 1. This is what we result in. If you choose to set the delta equals to 2 or 3, it's up to you, depending on your problem that you want to solve or the application. So this is the effect. These are the plots of when you tune delta. So that's it for the Huber loss. Thank you very much, and I'll see you next time.